Airplanes and windmills use propellers. But their propellers do different things. The propellers of airplanes move the airplanes forwards. The propellers of windmills extract energy from the wind and use it for turning their electric generators, while the windmill stays at the same place. The propeller of Blackbird, a wind-powered car, which does not use any electricity, is a combination of the two. It moves Blackbird forwards like an airplane's propeller, and it extracts energy from the wind, like a windmill's propeller. Blackbird's propeller accomplishes those tasks due to its aerodynamic design and due to the clever mechanical design of Blackbird. A recent posting in YouTube showed Blackbird moving downwind 3 times faster than the wind that was pushing it. This is mind-boggling. Here, I'll explain how Blackbird has achieved such remarkable performance. I'll focus only on the mechanical design. My explanations rely on principles of physics and air properties. Links to finer details of the explanations provided here are given at the end of the presentation. My explanations are different from some explanations that are circulating online. This is a back view of Blackbird. The arrow points to the link chain that connects the shaft of the propeller to the rear wheels. Here, inside the body of Blackbird, is hidden the secret of the amazing performance of Blackbird, the ability to start from rest and to run downwind and upwind faster than the wind. And to do it with one propeller that acts as an airplane propeller and as a windmill propeller. A gear, similar to a bicycle gear. It connects the propeller and the rear wheels of Blackbird so that they rotate as one unit. Their individual rotation velocities, though, are determined by the selected gear ratio, as in bicycles. In the following, we'll see how the gear makes the entire operation of Blackbird possible. Here is my explanation. The propeller splits the wind force into 2 forces, translational, which pushes the propeller forwards, and a rotational, which turns the propeller around its axis. Those forces are relayed to the wheels. The translational force pulls the shaft forwards. This force is transmitted through the chassis and pushes the axle of the wheels forwards, which pushes Blackbird. The rotational force turns the shaft of the propeller, which turns the gear, which applies a torque on the wheels, which triggers the reaction of the ground friction, which applies a force on the axle, which pushes Blackbird. The translational and rotational forces together act on the axle of Blackbird and push it forwards. These 2 forces get all their energy from the wind. This situation is similar to a car stuck in the sand. To get it out, the driver keeps the wheels turning by the force of the motor, while people outside are pushing it from behind. Both the rotational force of the wheels and the translational force of the people contribute to moving the car forwards. The total force that pushes the car forwards is the sum of those 2 forces. As we have seen, the propeller divides the wind force into 2 parts, the translational and rotational. These 2 forces together push the axle of Blackbird. When Blackbird is at rest, these 2 forces are weaker than the opposing internal friction force of Blackbird, and Blackbird won't move. When the propeller is connected to the wheels of Blackbird by the gear, the augmented rotational force, together with the translational force, becomes stronger than the opposing forces. As a result, Blackbird accelerates a little bit, the blue arrow with the A. Due to the motion of Blackbird, the propeller spins a little faster, and the apparent wind that acts on the propeller increases. That creates stronger translational and rotational forces, and as a result, Blackbird's acceleration increases. And the cycle continues. To get insights on the finer details of Blackbird's dynamics, we introduce an XYZ coordinate system. The car moves and the wind blows in the X direction. Let's look at the relationships between the 3 velocities that play different parts in Blackbird's motion: the true wind velocity, the apparent wind velocity in the X direction, and Blackbird's velocity. At the start, the car is at rest. The apparent wind velocity, blue arrow, is equal to the true wind velocity, green arrow. As the car starts moving, orange arrow, the apparent wind velocity decreases. The true wind velocity does not change. That goes on till the car moves at the wind's true velocity. At that point, the apparent wind velocity becomes 0. When the car moves faster than the wind, the direction of the apparent wind is reversed and points against the car's velocity. As the car keeps moving faster against the apparent wind, the magnitude of the apparent wind velocity, blue arrow, keeps increasing, pointing against the car. Now, we have to understand the relationships between the propeller's spinning and the apparent wind velocity that its parts are experiencing. When viewed from the front, the propeller spins counterclockwise in the YZ plane, as indicated by the yellow arrows. The propeller has two identical blades. We'll dub one blade brown and the other orange. Each blade can be viewed as made of cross-sectional profiles, brown and orange, correspondingly. We use the term profile, rather than airfoil, to indicate that we mean a cross-sectional part of the larger airfoil, the blade, the propeller, or the wing. Each brown profile has a symmetric orange profile. Two symmetric profiles have the same shape and the same angle with respect to the YZ plane. Profiles close to the center of the propeller will be called inner. Profiles close to the tip of the propeller will be called outer. When viewed from the front of Blackbird, profiles trace circular paths in the YZ plane. Their velocity vectors in the YZ plane are tangential to their circular paths, brown arrows. Since the true wind blows in the x direction, there is no wind in the YZ plane. Therefore, the tangential apparent wind experienced by a profile at any moment would be of the same magnitude and of opposite direction to the profile's tangential velocity at that moment. Pairs of brown and blue arrows. When the propeller is in the vertical position, the y direction and the tangential direction of its vectors are the same. It is convenient to analyze relationships between vectors when the propeller is in the vertical position. In our discussions, we will analyze vertical propellers. All our conclusions will also be valid for any propeller's position. The tangential velocity of a profile is proportional to its distance from the axis of the propeller. At any given moment, the tangential velocities of outer profiles is greater than those of inner profiles. This slide illustrates the three-dimensional configuration of two arbitrary symmetric profiles in the XYZ coordinate system. It shows the orientation of a brown and orange profiles in their XY planes for a vertical propeller. The brown arrows are the tangential velocities. The blue arrows are the tangential components of the apparent wind velocities. Theta is the angle that the profiles make with the YZ plane, the propeller's plane. Now that we have analyzed the components of the apparent wind and the spatial configuration of profiles, let's put it all together. The following slides are bird's-eye views of a vertical propeller. They illustrate how the total apparent wind hits an outer profile as Blackbird is accelerating. For reference, they also show the components of the x and tangential components of the apparent wind. Purple lines indicate the total apparent wind. Blue vertical arrow indicates the x component of the apparent wind. This component dwindles to zero as Blackbird approaches the true wind's velocity. Blue horizontal line indicates the tangential component of the apparent wind. This component keeps growing as the propeller spins faster. The green arrow indicates the true wind velocity that does not change. Let's look now at the development of the apparent wind as experienced by an arbitrary profile during the slower than the wind motion phase of Blackbird. We saw here that although the x component of the wind dwindled to zero, the disappearing left blue arrow, plenty of apparent wind, the purple line, was acting on the propeller. The spinning of the propeller created a sidewise component of the apparent wind. The propeller extracted the energy for moving Blackbird from that resulting total apparent wind. That is the essence of the solution of the riddle of the dwindling wind. It is true that the apparent downwind dwindled to zero. However, the spinning of the propeller created a sidewise large component of apparent wind that, together with the dwindling downwind, accelerated Blackbird. Let's move now to faster than the wind motion. The striking part of this slide is that the x component of the apparent wind, the left blue arrow, was pointing against the direction of Blackbird's motion, and at the same time, the total apparent wind, the purple line, kept growing. It means that as Blackbird was moving downwind faster than the wind, it was actually moving diagonally against the apparent wind. This is reminiscent to sailboats that sail diagonally against the wind. Along the same lines, when Blackbird was moving slower than the wind, the apparent wind on its propeller was like that of a sailboat that is sailing downwind. During this phase, the total apparent wind changed its direction by 90 degrees. Also, at any instant, the apparent wind varies from one profile to its next. To sum it up, we have seen here how the smart mechanical design of Blackbird secured a continuous supply of strong apparent wind to the propeller. Sufficient apparent wind was available to the propeller throughout Blackbird's motion, starting from rest and then when Blackbird moved slower and faster than the wind. The smart aerodynamic design of the propeller utilized the supplied apparent wind. The twist of the blades and the selection of its profiles extracted the energy from the apparent wind, as the apparent wind changed its angle of attack and strength. All the energy that Blackbird used was extracted from the wind. The rotation of the wheels did not extract any energy from the ground. Due to the design of Blackbird, part of the wind energy moved Blackbird forwards, and part spin the propeller. The playlist How Blackbird Works has more videos about this topic. If you liked this presentation, please give us a like. If you would like to be notified about other posts of similar nature, please subscribe. Thank you.